So if you look at the liquid-liquid extraction and solid phase extraction, where two different liquids are used in order to perform the extraction in solvent extraction or liquid-liquid extraction. Selective transfer of the solute from one liquid phase to another liquid phase was seen in liquid-liquid extraction, whereas in solid phase extraction, the selective transfer of the solute from liquid phase to solid phase we have seen, and solid phase what we will be using will be most probably the sorbents, and a variety of the types of the interactions we can see which will be responsible for the separation of the solute molecules, and the solutes will possess different affinities towards the extraction media, therefore the solute molecules are getting separated. So under this background, we will utilize some special substances or fluids which are known as supercritical fluids in order to perform the extraction process, and even the supercritical fluids are used to perform the separations by chromatographic technique. If you use supercritical fluid in the extraction technique, the extraction will be supercritical fluid extraction, and if you use supercritical fluid as a mobile phase instead of gaseous or liquid mobile phase in GC or LC, the technique is called as supercritical fluid chromatography. So under this supercritical fluid extraction, the extraction process is going to be performed in order to separate the solutes. Maybe matrices present in the sample or analytes will be present in the sample. The aim of or the objective of the separation is to exclude the matrices or to exclude the analytes, and that is dependent upon the concentration of the matrices or concentration of the analytes. So in today's talk, we will cover definition of supercritical fluids, what are the properties exhibited by the supercritical fluids, what are the advantages of supercritical fluids, how we are going to utilize the supercritical fluids in order to perform the extraction, and instrumentation of supercritical fluid extraction, and some of the applications of supercritical fluid extraction. So supercritical fluid, when you look at the property or the nature of the supercritical fluid, it is just like a special substance and which is utilized in order to perform the extraction process. We can see the property of supercritical fluid with respect to effusion and dissolution ability. You can compare the effusion rate of the supercritical fluids just like a gas. Whenever you interact the supercritical fluid along with the solid and the supercritical fluid will be mixed in such a way that the mixing of gaseous and solid substances. And that solid, whatever you have added into the supercritical fluid, that will be comfortably dissolving just like a dissolution of that particular solid in the liquid. So such a special property the supercritical fluid will be possessing. So what is the definition of supercritical fluid? It is very, very important. Here I have presented a phase diagram, and this phase diagram explains the effect of temperature and the pressure on the states of the substance. So what are the different states of the substance obtained after raising the temperature and after raising the pressure? So normally the substances or the matter can be classified into three types: solids, liquids, and gases. Solids, liquids, and gases are the three states of matters. So solids will be existing at very low temperature and pressure, and liquids will be existing intermediate, and vapor forms or gaseous forms of the matter will be existing at higher temperature as well as at vapor pressure. Vapor pressure. So there is a existing of critical point for every substance. Critical point is existing. What is this critical point? You can see here, this is a phase boundary between the solid and the vapor state. Liquid is existing. Between liquid and the vapor state or gaseous state, there is a boundary. There is a boundary. So you can convert solid into liquid by simply raising the temperature and pressure, and ultimately liquid to vapor state. By raising the temperature extremely, you can convert liquid to vapor state or gaseous state. Before undergoing ionization, the liquid can be converted into vapor state. So these two states, liquid states and vapor states, they cannot be distinguishable. the liquid state or vapor states of any matter of any substance cannot be distinguished at a particular temperature and pressure. So the temperature at this point is called as critical temperature, and the pressure at this point is called as vapor pressure or critical pressure. Critical pressure means there is a critical point. Critical point means at the critical temperature and pressure. At the critical temperature and pressure, there is a critical point. So when you bring a substance above its critical temperature and pressure, the liquid or gaseous state do not exist. The liquid or gaseous state do not exist. Straight away we can say that a supercritical fluid is a substance which is obtained by bringing the pressure and the temperature above their critical values. So a temperature above the critical point and the pressure above the critical point, the substance which is known as supercritical substance, a supercritical fluid. So liquid and gaseous state, these are the terminal states, and the intermediate state is going to be the supercritical fluid state. So the supercritical fluids will have excellent properties when compared to liquids and gases. So we can say that the properties of supercritical fluids will be always in between the properties of liquids and gaseous species. So when you use supercritical fluids, the supercritical fluids will effuse like gases through the solids. So when you make them to interact with the solids, they will effuse like gases. Their movement will be very, very comfortable. And the dissolution of the matter in these supercritical fluids will be just like the dissolution of the matter in the liquids. So they possess excellent properties at critical point, and this critical point is going to teach us what is the meaning of critical temperature or critical pressure. Critical temperature is nothing but it is a temperature above which the gaseous state is not going to be existed or liquid state persists. The critical temperature is nothing but it is a temperature beyond which the distinct liquid phase of a substance will not exist. That is called as critical temperature. And the pressure, when it is raised, in order to convert the liquid to vapor, that pressure is called as vapor pressure, and the critical pressure will be beyond the vapor pressure. So this temperature and pressure is going to be very, very important in converting the matter into supercritical fluid. So supercritical fluid is a substance at a temperature and pressure above critical point. This is going to be the critical point. Liquid phase do not exist, and the substance is going to be converted into supercritical fluid. Supercritical fluids effuse through solids like a gas and dissolve materials like a liquid. So they're very close to critical point. Small changes in temperature or pressure results in large changes in density, and this change in density will become responsible for the behavior of these supercritical fluids in order to diffuse or in order to dissolve or in order to perform, in order to initiate the interaction with the solute molecules or whatever it is. So this is about the definition of supercritical fluid. Here I have presented the three photographs of supercritical fluid, how we are going to get the supercritical fluid when a substance is going to be heated. So subcritical state, supercritical state, you must have the ability to distinguish between subcritical and supercritical state. In a subcritical state, it is a before the critical point. Before the critical point, there is a phase boundary is existing at the subcritical state. So there is a phase boundary existing, means the liquid is about to be converted into supercritical fluid state, not to the gaseous state. The liquid is going to be converted into supercritical fluid state. So when you keep on increasing the pressure, the phase boundary between these two states is going to disappear, and ultimately the supercritical fluid is going to be formed. So initially there will be a phase boundary. As explained in the phase diagram, there will be a phase boundary, and in between liquids and gases, supercritical fluid will be existing with respect to its property. So if you increase the pressure, regardless of the temperature, regardless of the temperature. The phase boundary line is going to be diminished, going to be destroyed in order to convert the subcritical fluid to supercritical fluid. And the fluid in this particular state will be having the property of viscosity, density, and diffusion coefficient, always in intermediate to liquids and gases. Therefore, the supercritical fluids will become highly advantageous in order to perform the separation process, either by extraction technique or chromatographic technique. So the forces from the kinetic energy of the molecules will exceed when the supercritical fluid state is attained. So why the supercritical fluids are used, where these supercritical fluids exists? When the forces from the kinetic energy of the molecules will be exceeding from the forces from condensing influence of the intermolecular forces. Therefore, the supercritical fluid state will be existing. Kinetic energy is associated with the movement of the molecules, and this kinetic energy, due to the movement of the molecules, when they have attained the state of supercritical fluid, at that particular state, the kinetic energy is going to become larger when compared to the forces from the condensing influence of the intermolecular forces. So the forces due to kinetic energy will become larger when compared to intermolecular forces. Therefore, the supercritical fluid state will be existing. So with this particular background, supercritical fluid states are going to be very, very important. So we can explain the supercritical fluids with the properties such as higher densities, excellent diffusivities with the diffusion coefficients, satisfactory viscosities when compared to liquids and gases. The diffusivity coefficient and densities and viscosities will be in between those of liquids and gases. Therefore, these supercritical fluids are employed as excellent solvents in order to perform the separation either by extraction process or by chromatographic technique. Other advantages, important advantages of these supercritical fluids are they are inexpensive. So we need not to use any sophisticated technique in order to produce a supercritical fluid. Just we need an instrument to raise the temperature or to raise the pressure. So inexpensive technique will be employed in order to generate the supercritical fluid. And these supercritical fluids are not harmful, they are harmless, they are innocuous, they are harmless, and even they are non-toxic. Therefore, we can use these supercritical fluids to any extent in order to perform the separation process. And the advantages of making supercritical fluids to escalate into the atmosphere by just releasing the pressure, the recovery of the analyte will become trivial, will become very easy. So we can destroy the supercritical fluid state by simply releasing the pressure. And when we disturb the pressure beyond its critical point, the supercritical state is going to be destroyed. It is going to be diminished, and only analyte can be collected in the collector device. Therefore, easy recovery of the analyte can be seen. So higher densities, solute diffusivities, and viscosities are the three important properties of supercritical fluids. These properties are intermediate between gaseous and liquids, as you can see in this particular table. If you look at the density of supercritical fluids, 0.2 to 0.5 gram per ml, the density of supercritical fluids, most of the supercritical fluids, if you consider, the density will be 0.2 to 0.5 gram per ml. If you consider gaseous species at standard temperature and pressure, 0.6 into 10 power minus 3 to 2 into 10 power minus 3, whereas for liquids, 0.6 to 2. So this is going to be the intermediate value between this. So gases are having lower density, liquids are having higher density, but the supercritical fluids are having intermediate densities, larger densities, we can say. And the diffusion coefficient, you can see very, very less diffusion coefficient when compared to gaseous species, but slightly large when compared to the diffusion coefficient of the liquids. Therefore, the solute diffusivities into the supercritical fluid will become excellent. That's what the effusion of the supercritical fluids through the solids, just like gases, we can see. And you can see the viscosity, 1 to 3 into 10 power minus 4. Liquids are having higher viscosity, and the gaseous species are also having the same viscosity when compared to the supercritical fluids. So whenever the viscosity is less, the movement of the fluid or movement of the substances can be initiated by applying the pressure. So pressure influence can be seen to a greater extent. Therefore, these supercritical fluids will be exhibiting more and more advantages in performing the separation process. So supercritical fluids will be having higher densities, a lower diffusion coefficients than gaseous spaces, or higher diffusion coefficients than liquids, and viscosities, which are in the same order of magnitude when compared to gaseous spaces, but lesser when compared to liquids. Therefore, these properties make the supercritical fluids as advantageous fluids. Because of the high density of the supercritical fluids, these fluids are used to dissolve large number of non-volatile molecules because none of the solvents will become satisfactory for the dissolution of non-volatile molecules. When you compare supercritical carbon dioxide, if you take carbon dioxide is easily available. There is no any difficulty arised in producing the carbon dioxide, and even producing the supercritical carbon dioxide is not at all a difficult job. So if you use supercritical carbon dioxide, you can make many alkanes, many n-alkanes containing 5 to 22 carbon atoms to dissolve in supercritical carbon dioxide, not only for the dissolution process, but also for the separation process. Supercritical carbon dioxide can be used. So supercritical carbon dioxide will be a best solvent for the dissolution of n-alkanes containing 5 to 22 carbon atoms. And even di-n-alkylphthalates containing 4 to 16 carbon atoms are easily soluble in supercritical carbon dioxide. And when you look at the polycyclic aromatic hydrocarbons with the several aromatic rings, they are mostly insoluble in many commonly used solvents, but the supercritical carbon dioxide will become excellent solvent, selective solvent for the dissolution of polycyclic aromatic hydrocarbons. As a result of these excellent properties, two popular applications are seen, especially in the separation science, that is decaffeination of coffee beans. Decaffeination of coffee beans will be done particularly by the supercritical fluid extraction process. And even the removal of nicotine from cigarette tobacco will also be performed by using supercritical extraction technique by using supercritical carbon dioxide as a fluid. So caffeine can be extracted from coffee beans by using the supercritical fluid extraction. And similarly, the nicotine from cigarette tobacco can also be extracted by means of the supercritical fluid extraction. Let me explain this at the last. So once we complete the discussion on the supercritical fluid extraction, soon after the instrumentation process, so we shall discuss on the extraction of caffeine from coffee beans as an important application. So you should remember about the density, that because of the density, most non-volatile components are soluble in supercritical fluids such as supercritical carbon dioxide because of the density of 0.2 to 0.5. The density is very large when compared to gaseous spaces. So 0.6 to 2 into 10 power minus 3 is going to be the density for gaseous fluids, whereas supercritical fluids will exhibit 0.2 to 0.5, very large density when compared to gaseous spaces, and this large density will make these non-volatiles to dissolve in supercritical fluids. So as an important application, you can remember about the percentage of decaffeination. 97 to 99% of the caffeine can be extracted by this technique. Let us see that later. And as I told you, easy recovery of the analyte is always possible in this supercritical fluid extraction, because we can allow the system to become to the equilibrium state by simply releasing the pressure, as well as the temperature. So we have adjusted the temperature above its critical point, and even commonly pressure has been adjusted to above its critical point. If you disturb that critical point, critical pressure and critical temperature have been disturbed. So supercritical fluid state will be destroyed. The carbon dioxide will be escalated into the atmosphere, so that if you have any collector flask under the ambient temperature, the collector flask will be having the analyte. So whatever the sample you have subjected for separation process, the matrices will be left over and the analyte taken out from the supercritical fluid, that will be made to be dissolved in a suitable solvent, into which a flow capillary will be immersed in the instrumentation part. Let us concentrate on them later. So by simply allowing the solution to equilibrate with the atmosphere at relatively low temperature, we can easily recover the analyte. So by reducing the pressure and allowing the fluid to evaporate under the ambient lab conditions, we can procure the analyte into the collector vessel or collection flask. So collection flask is containing only solvent, which is becoming more suitable for the dissolution of the analyte which has been extracted. Supercritical fluid will be escalated, will be escaped to the atmosphere. So supercritical fluid is not going to be retained in the solvent. It is not going to be retained in the solvent. Therefore, easy recovery of the analyte can be seen. And as I told you, if you use supercritical carbon dioxide, it is not a high cost fluid. We need not to pay anything in order to procure the carbon dioxide. So if we have some traditional technique, we can procure the carbon dioxide by ourselves. We need not to use any special devices in order to procure the carbon dioxide. If we have a compressor bag, we can procure the carbon dioxide into the compressor bag and we can store it. So therefore, supercritical carbon dioxide or any supercritical fluids are inexpensive. They don't require more cost, and they are harmless. They are harmless. They are innocuous. They are non-toxic. They are not going to affect the human being. They are not going to affect the separation scientist in order to become ill, in order to become sick. So the properties exhibited by many other organic solvents are not exhibited by the supercritical fluids. Only density, viscosity, and the diffusion coefficient. These are the properties, and these properties are more than enough to exhibit high extractability or high extraction efficiency in extraction techniques while using these supercritical fluids. So let us go to the solute diffusivities next. Solute diffusivities. The diffusivities are in the order of higher magnitude than liquids. So 0.2 to 2 into 10 power minus 5, 0.2 into 10 power minus 5 to 2 into 10 power minus 5 centimeters square per second is the general range of diffusion coefficient for liquids. But for gases, 1 into 10 power minus 1 means 0.1 to 0.4. 0.1 to 0.4 is the diffusion coefficient of gaseous species. Whereas the supercritical fluids are having the diffusion coefficients of 0.0012 to 1 into 10 power minus 4 centimeters square per second. So when you compare with the liquids, almost we can say roughly 10 times, 10 times larger than the liquids. This larger diffusion coefficient of supercritical fluids will make easy dissolution of the matter, easy dissolution of the components or the solutes in supercritical fluids. So therefore, because of the intermediate property of diffusion coefficient or intermediate value of diffusion coefficient of the supercritical fluid, the solubility or the dissolution rate of the substances in supercritical fluid will become excellent. So as a result of this, the extractability into this supercritical fluid from any of the solvent which you have used for the dissolution of the sample will become very easy, very common, very simple. Therefore, supercritical fluids are always advantageous to use in order to perform the extraction process. And next, you can see the viscosity. The viscosity will be order of lower magnitude when compared to liquids. So the viscosity of the supercritical fluids will be lower when compared to liquids. So you take water, you take methanol, you take acetonitrile, you take DMF, you take ammonia, and similarly you can take acetic acid, you can take formic acid, whatever it is. They have viscosities of higher values, higher magnitude. When you take gaseous species 1 into 10 power minus 4 to 4 into 10 power minus 4, so somewhat larger than the supercritical fluids, where the viscosity of the supercritical fluid will be from 1 into 10 power minus 4 to 3 into 10 power minus 4. Means, because of this lower viscosity of the supercritical fluids, it will become very easy to apply the pressure in order to convert the fluid into supercritical fluid. Therefore, the density, diffusion coefficient, and viscosity, these three properties will make the fluids, will make the substances for their use as an extraction medium in order to increase the extraction efficiency, where we cannot achieve the required extraction efficiency by either liquid-liquid extraction or solid phase extraction. So supercritical fluid is nothing but it is a substance existing above the critical temperature and pressure. When a substance is brought to above its critical temperature and pressure, the state of supercritical fluid is obtained with the varied properties such as density, diffusion coefficient, and viscosity. The density of supercritical fluids will be always larger than the gaseous phases, and the diffusion coefficient of the supercritical fluid will be larger than the liquids, and the viscosity of the supercritical fluid will be lower than the liquids. Therefore, the property of the supercritical fluid in order to effuse through the solids just like a gas and to dissolve the substances just like the liquid will become excellent. So supercritical fluids, no techniques are available in pharma industry or food industries. Even the ingredients present in the products can be removed easily by this supercritical fluid chromatographic technique.